Hello everybody. Uh, Let us start the, I think this is the last chapter or last module of Introduction to Crystal Elasticity and Crystal Plasticity. So in this module, we will try to focus on the multiscale approach, basically the multiscale modeling approach. So in this chapter or in this module, probably I will try to focus on that very introductory level of the multiscale modeling approach, and of course is very specific to materials modeling, although this is a very vast content for multiscale modeling approach. So we will try to focus on very selective things and very basic elementary things related to multiscale modeling approach to get some idea about the topic. So here the objective is not much in going into details of the or depth analysis of the different approaches of the multiscale modeling, rather to understand the subject little bit in easier way. So multiscale means we understand that the modeling approach at different length scale or at different time scales. But problem is that the how to link the different length scale and different time scale, and what may be the consequence of the computational cost to do such different scales of modeling approach at a single times. So let us see how we can start with this. So before start of this actual discussion on the multiscale modeling approach, I try to acknowledge the following professors, scientists, technicians, because this module I have prepared based on the view of these distinguished scientists and the professors, and I will try to represent their view on the multiscale modeling approach. So first, if we see that multiscale modeling approach means how we can conduct the physical model of the process at different time scale or at different length scale. If we see, this is the very four basic slabs of the multiscale modeling approach. You see that of course all these cases the length scale and time scales are different. So first we can start with the electronic structure, atomistic structure, then next level of the length scale is the microstructure, and finally the continuum model. Probably we are very much familiar with the modeling approach using the continuum mechanics or in the continuum scale. And here the continuum scale means we understand around order of millimeter range, but if we look in back the electronic structure, the length scale is almost around on the level of 10 to the power minus 10 or 10 to the minus 12, like that. So there is huge difference in the length scale between the electronic structure and the continuum scale. And in between there is a atomistic structure and the microstructure. They exist at the different scale, and if we see the electronic structure, generally we explain that in some kind of using some statistical mechanics or statistical model, or we can say the analytical model, and we try to understand the electronic structure, and then we try to looking into the electronic structure we can predict the atomistic structure using the concept of the molecular dynamics, or we use the Monte Carlo simulation method also to predict the atomistic structure by understanding the basic physics of this. But when you approach the next level of the length scale, microstructure scale, probably we can analyze the microstructure using the finite element method or some kind of constitutive law. We use it, and we can analyze in some other numerical techniques also, some analytical, semi-analytical techniques we can use for microstructure. But of course when you next level of this thing continuum, we link it that CFD, computational fluid dynamics, or some other finite volume methods probably we can use, or even we can use the finite element method, and to analyze the process in the continuum scale. So it is also important to know that probably it will be the experimental facility, or probably the conducting the experiment is relatively costly if we try to do in the lower scale, probably electronic structure atomistic. In that case, in that scale, to conduct the experiment is bit of costly, time consuming, and uncertainty also involvement is more. But rather, if it is possible to conduct the experiments on the continuum scale, or probably we can see the doing the experiment on the microstructure in that scale level, it will be relatively low costly. So predicting the experimental results, or using the experimental results to predict the behavior of the materials in the lower scale or probably in the upper scale, that needs to follow some relations, or maybe some organized approach is possible through the multiscale simulation among the different length scale. Probably it can go upper side upscaling, or it is possible to do the low scale downscaling also. Both way it may be possible to develop some multiscale approach for the different processes. So if we look into that basic of the approach in the large multiscale modeling approach, if we see from the figure that probably if we consider the dynamics of metals, and we can start with at the length scale in the dislocation phenomena. So dislocation phenomena, we can explain the edge dislocation, screw dislocation on the atomistic scale, and from that we can predict the dislocation exists in a crystal structure. And of course these defects or dislocations actually exist due to the due consideration of the, we can assume that there is a defects exist in this in the atomic structure of a specific material, and there we can estimate finally the basic elementary in terms of edge and screw dislocation for any kind of single crystal structure. Now here we can predict the dislocation motion and interaction between the dislocations, and then how as dislocation energy interaction, or probably there is exchange of the dislocation energy due to the motion of the dislocation, probably that we have explained using the single crystal plasticity that is related to the dislocation dynamics. And here we can predict the single crystal stress strain relationship, whether it is isotropic or anisotropic. But if we, in this case, single crystal plasticity, probably if we look into the most of the cases, we consider the anisotropic elastic or anisotropic plastic behavior of the materials. So looking into the dislocation dynamics, probably we can link in the next level the polycrystalline plasticity. If you see that polycrystalline plasticity, that is in the mesoscale, the scale is different from the dislocation dynamics and as compared to the polycrystalline plasticity. So looking into the single crystal plasticity by averaging all these things, maybe we can predict the plastic rule, or we can derive the plasticity model in case of polycrystalline structure. But that scale is, even it is in mesoscale. So probably we can polycrystalline stress strain response or polycrystalline stress strain relations can also be derived on this scale. But finally, next level scale of analysis is the probably that is a continuum scale. So at the continuum scale, probably we can represent the stress between the stress and strain in terms of using the different plastic law. So we have discussed the continuum plasticity model also, and we derived that these models consider both isotropic behavior or anisotropic behavior in aggregate, but this model is valid over the continuum scale, that means over the around scale of the millimeter, order of the millimeter range. So in this case we estimated the von Mises ill surface, and then from there we can predict the plastic behavior of the materials. So probably the single crystal plasticity is the key fact to link the atomistic scale and the continuum length scale. But how we can link between these two scales, That is most important in the multiscale modeling approach. Now, if we look into that basic idea on the materials modeling and how we can use the multiscale approach in materials modeling. So, if you see that window of the dislocation plasticity, the resolution is like that. First, we can start with the atomistic model, the molecular dynamics. It's a specific points where we can fix all the atoms, and the length scale is around 10 to the power minus 10 meter. And from the atomistic model, we predict the defects, and then we represent within the materials in terms of the dislocations. But that dislocations is we consider as a discrete dislocations. So, discrete dislocation theory, probably we can use it on this scale, and where the scale range is around or of the order of 10 to the power minus 8 meter. And looking into the discrete dislocations theory, we can predict the continuously distributed dislocation theory. So, here we can predict the dislocation pattern as a whole, and the length scale in this in this analysis is probably it is more. So, it is around 10 to the power minus 7 meter, and then once the next level of the scale, the crystal plasticity, and we can analyze the over the individual grains also, or or as an aggregate for polycrystalline theory also we can use the plastic laws or deformation behavior of the grains. But within the grains we can use the information of the nature of the dislocation existence here. So, but here in this case the length scale is around 10 to the power minus 5 meter, and finally we can analyze this macro scale, or maybe using the continuum plasticity law we can predict the plastic behavior of the material. So, in this there is a different theories exist over the different length scale, and finally when you try to estimate the plastic behavior of the material in the macro scale or continuum in using the continuum plasticity model, probably it behavior is the averaging of all the previous scale of the analysis. Now, if you see the polycrystalline idealization grains with the distributed defects, probably in this case the distributed defects in terms of dislocation. So, in this case we can see that both scales of grain and subgrain structures, there is a, this is the probably interaction through the grain boundary, and that is the interaction, that is also the interaction through the grain boundary. But how we can represents the behavior of the dislocation within the structure, and in this case we represents the behavior in the scales of the grain and the subgrain structure. And of course, then when we represent this on only grain scale, in this case all the heterogeneities also exist within the grain scale, and finally represents the as an aggregate, that is a homogenization description of the materials also occurs in this final case, and that is the aggregate behavior of the polycrystals, which is the aggregate of the individual behavior of the single crystal structure. So, these are the ways, different way or different window of the analysis at the different scale, and we have not looked into that. Probably how we can link between all these scales. So, what is the importance of multiscale methods? But nowadays the limitation of the industrial simulation is, first thing is that of course most of the cases we focus on the continuum models. They are good even, but they are not always adequate. Probably if we consider the problem of the fracture and failure of the solids, that actually required till now the improved constitutive models to describe the material behavior. But macroscopic material properties of the new materials and composites are not readily available, but that is very much needed in simulation based designs. So, that actually, of course, in this case specifically when the composites, if we consider our new materials, So it is very difficult to predict the behavior of the continuum scale until or unless we can analyze the behavior of the materials in the lower scale. So detailed atomistic information is required in the regions of the high deformation, or if there exists discontinuity. Probably that is more relevant to the composite materials. So that is more restricted use of the this is the restricted use of the continuum models. Now, if we on the other side, if we look into that molecular dynamic simulation, that is also limited to very small domain, 10 to the power 6 to 10 to the power 8 atoms, probably represents the behavior of the materials as a whole, and the small time frame also in the order of the nanosecond time scale, we can predict the behavior using the molecular dynamic simulation. But experiments even on the nanosystems involve much larger system over, and at the same time over a large time also required to conduct the experiments. So that are the another limitation of the simulation if we consider the molecular dynamics of the for new materials or new system. But opportunities obtain material properties probably by subscale, multiscale simulation, that can also be done. Enrich information about the material or structural performance across scales, that can be done by concurrent multiscale methodologies. So that is other ways probably we can look into these two aspects to explore the multiscale methods or multiscale modeling approach in material science. So to do that, that means to analyze the multiscale modeling approach, probably we need to understand that what are the approaches that we generally follow in case of multiscale modeling. One is the hierarchical approach, another is the concurrent approach. So hierarchical approach, we use the known information at one scale to generate model for the larger scale. So information passing typically through some sort of the averaging process from lower scale to the next level of the scales. Examples: bonding models, potential and very other things. The constitutive laws probably use in case of hierarchical approach. But concurrent approach, we perform generally simulations at different length scales simultaneously. So relationship between the length scale are dynamic. One typical example of the concurrent approach is the specifically heat bath techniques. Let us see that what is the heat bath techniques. So heat bath techniques probably used for the calculation of the thermal properties. Using the canonical description of the statistical mechanics, one calculates by the numerical or computer based techniques. So one such example of these things, Monte Carlo methods, that randomly change the configuration of a system and accept or reject it according to the probability function. If we do for iterative process, on average this leads to the thermal equilibrium property. So this is the typical heat bath techniques that actually follow the concurrent approach to predict the thermal properties. But in this case we need a perform simulation at the different scales, and most of the cases we need to some iterative approach to trial and error kind of things. But main difficulties of concurrent approach is that the length scale, the relationship between the length scale are dynamic, or to maintain the dynamic behavior at the interface is really difficult to multiscale modeling approach. So most of the methods now probably it is more easier to go to the hierarchical approach, where the information in the lower scale can be used to predict the behavior on the upper scale. So these are the typical approaches in multiscale modeling. Let us start with the atomistic methods. In this case, we use the empirical relation, and from the very beginning derived the force fields together with the semi-classical statistical mechanics to determine the thermodynamics and transport properties of the system. But the statistical mechanics solve actually exactly. So of course the atomistic methods use the empirical derived force fields, but it can solve exactly the data, or what may be the advantages and one sided and other sided of the atomistic method. First one is that it can be used to determine the microscopic structure of more complex systems, probably on the order of 10 to the 4 to 6 atoms of this that constitute one system, and using that system the microscopic structure of the system can also be calculated. But these models can also be dynamical process. Consider the dynamical processes probably on the up to longer time scale, up to order of 1 microsecond. But other side, if you look at the atomistic methods, but results intuitively depends on the quality of the force field used to represent the system. So it's a system dependent. The many physical processes happens on the length and time scales inaccessible probably by these methods. For example, the diffusion in solids, many chemical reaction, protein foldings, these type of physical processes probably difficult to access using these atomistic methods. So that is the other sides of this atomistic methods. Now if we look into that, mesoscale methods that actually introduce simplification to the atomistic methods to remove the first degree of freedom and consider group of atoms as individual entities interacting through the effective potentials. That means the cluster of a very group of atoms represents one properties, one state, and that can be considered in the mesoscale method. So probably this mesoscale method is the higher scale approach, higher scale in the sense that scale length is bigger here as compared to the atomistic scale. So the advantage probably can be used to the study structural features of the complex system. So in this case the cluster of atoms or group of atoms can be considered of the order of 10 to the power 8 to 9 atoms to represent the system. But dynamical process on time scale inaccessible to the classical methods even up to the 1 second. So probably we can use the larger time scale using the mesoscale methods. But disadvantage or other side, darker side of these methods is that it's often described only the qualitative tendencies. The quality of quantitative results may be difficult to ascertain sometimes. In many cases, the approximation introduced limit the ability to the physical interpret the results. So these are the two disadvantage probably if we consider the mesoscale methods. Now continuum methods. In this case we assume that matter is continuous and treat the properties of the system as field quantities. Numerically solve the balance equilibrium equations coupled with the phenomenological equations to predict the properties of the system. So this is the basic method of the continuum, basic philosophy of the continuum methods. But it in principle it can handle system of any macro size and dynamic process relatively longer time scale. So longer time scale as well as the length scale, longer length scale, it can handle the problem, and it is possible to solve the numerically balanced equation. We generally solve the numerically balanced equation, governing equation, we solve it on this scale. But difficulties is that required input, for example elastic tensor, diffusion coefficient equations of the state from experiment, or that can be derived from the lower scale methods, which sometimes is difficult to obtain, but cannot explain results that depend on the electronic or the molecular level of the detail. So of course continuum methods having advantage in one scale, probably it cannot capture the behavior of the system in the molecular levels in details or the electronic structure in detail. So in that case we need to consider the lower scales method, probably in the atomistic scale model we need to consider. Now of course there are the different scales of analysis, and each and every scales having their limitations or their advantages in the different way. But most important or significant things in the multiscale modeling is that how we can connect at the different length scale. So probably one approach that is normally called is upscaling methods. So in this case, using results from a lower scale calculation to obtain the parameters for a higher scale method. This is relatively easy to do, and it is generally called a deductive approach. Maybe we can look into the example to understand this, what is the upscaling method. One thing is that calculation of the phenomenological coefficients, for example the elastic tensor, viscosities, diffusivities from the atomistic simulations for later use in a continuum model. So this is one we generally used in case of upscaling. This is one example of the upscaling methods. Fitting of the force field using the initial results for later use in atomistic simulation. This is another example. We can use the fit the force field from the initial results of the for the later use in the atomistic simulation, and deriving the potential energy surface for a chemical reaction to be used in the atomistic molecular dynamic simulations, and deriving the coarse grain potential from the cluster of blobs of matter, or maybe can polycrystal from atomistic simulation to be used in the mesoscale simulation. So upscaling, all the upscaling method, that always we try to link the lower scale properties behavior in aggregate to link with the higher scale, or if there is a need of the any phenomenological behavior which is required, which need to define for the higher scale methods, that we can generally derive from the lower scale method. That is the basic philosophy of the upscaling methods. Similarly, in downscaling method, here the basic philosophy is the using the higher scale information. Most often it is experimental to build the parameters for the lower scale method, but it is more difficult as compared to the upscaling method because of the non-uniqueness of the problem. We can take some examples also. The results from a mesoscale simulation do not contain the atomistic detail, but it would be desirable to be able to use such results to return to the atomistic simulation level. That is called basically inductive approach. For example, fitting of the two electron integrals in semi-empirical electronic structure methods to experimental data, that is called ionization energies, electron affinities, etc. That is one example of this downscaling method. Fitting of the empirical force field to reproduce the experimental thermodynamic properties, for example second viral coefficient, saturated liquid density and vapor pressure. Probably if we consider, although theoretically it is difficult, more difficult downscaling approach to link the information from the higher scale to predict the behavior of the lower scale. But other way, probably if it is possible theoretically predict, so experimentally it is more easier to conduct the experiment relatively on the higher scale as compared to the lower scale methods. So in that way it is advantageous because here we need the information, or we can conduct the experiments on the higher scale. So looking into these two approaches, upscaling and downscaling in the multiscale modeling approach, now if we see that in general the multiscale modeling, the few significant points are important here. First point is that in many physical problems, several scales are present in space or time, probably caused by inhomogeneity of the medium or complexity of the mechanical process. So a fundamental approach is to first construct the microscale models and then deduce the macroscale laws and the constitutive relations by properly averaging over the microscale. So that if we look into that microscale and the mesoscale model here, if we see that basic fundamental approach of the multiscale modeling, linking that averaging of the lower scale and that use this information for the higher scale approach. The perturbation method of multiscales can be used to derive the averaging equations for a much larger scale from consideration of the small scale. So, in the mechanics of the multiscale media, the analytical scheme of upscaling is generally known as the theory of homogenization. So, ultimately, the more practical approach in the multiscale modeling is to consider the probably in the upscaling, which is relatively easier. Now we look into some example. Probably if we see the multiscale modeling approach, we take one example, that carbon nanotubes under tension, the atomistic results. If we see that first figure, that expansion to a larger system and longer simulation times actually allow exploration and discovery of the new behavior. So, if we allow for longer simulation time, probably we can do the simulation based design, we can explore new behaviors. Let us look into this example. At low strain values and high temperature, with that condition 5775 defect behaves as a dislocation loop. So, this 57 and this is the 75, these are this constitutive one dislocation loop here, made up of the two edge dislocation, that is 57 and the 75. Now, the two dislocation can migrate on the nanotube wall through a sequence of the bond rotation. So, through a sequence of the bond rotations, there is a glide direction. So, two dislocation can migrate separately through a if you look into the glide direction. So, in that direction actually two dislocations migrated here. So, that type of behavior, and that happens due to the sequence of the specific bond rotation in the carbon nanotube. So, that type of behavior probably it is due to the plastic behavior of the carbon nanotube. So, this is observed. So, final conclusion from here, that with this example we can say that if we longer simulation time if we allow, probably we can discover the very new behaviors. Okay, so, that can be model, and specifically when the carbon nanotube is subjected to some kind of tensile force. Now, if you look into the carbon nanotube under tension, the atomistic results, but if expansion to a larger system and longer simulation time, again if we do these things, if we see that under high tension and specifically low temperature condition, if we see the additional bond rotation finally leads to the larger defects and cleavage. So, that kind of actually finally leads to the related to the brittle behavior of the carbon nanotube. So, this behavior of the carbon nanotube, it is actually the simulation is done for the under tension. Now, under tension, what creates the dislocation, it can create the dislocation loop or movement of the dislocation, and finally with the, if tension is very high, probably you can subject it to some cleavage. So, that is very much obvious through this kind of simulation. So, that simulation having certain importance to predict the behavior of the carbon nanotube which is under tensile force. Now, this in this case, probably if it is a high tension and low temperature, this condition it predicts the behavior like the brittle behavior, whereas if in case of the tension, moderate tension, probably it can predict the plastic behavior of the carbon nanotube. So, these are the typical examples for this of the simulation based design generally we generally observe in case of multiscale approach. Now, this also the carbon nanotubes under compression, but this is a mesoscale result. So, scale is different here. So, expansion to a mesoscopic system through finite element methods parameters are modeled upon atomistic, but what was the initial calculation? If we see that axial compression simulation of the 9 walls of the carbon nanotubes and stress in the axial direction, if we see the simulation, that color actually predict the different deformation behavior corresponding to the different stress level and axial direction. So, point is here that the simulation can be done in the different scale, but here the I think it was in the different scale, but here if we conduct the experiment in the mesoscale, so to predict the different behavior, and that can be possible if we consider the different multiscale approach here. Now, in general, if we see that multiscale modeling of the materials, so always we try to understand the molecular level origins of the material behavior, but predict the behavior of the materials from the first principle. So, if we see also that along the x-axis and y-axis, if we see that the length scale are different, time scale are also different. So, in the lower scale, femtosecond, or maybe in the nanometer range, nanometer length scale and the femtosecond time scale, that can predict the behavior of the electrons, and as a whole, next level, the molecular dynamics, the behavior of the atoms as a whole. Then using the behavior of the atoms, probably we can the mesoscale, mesoparticles behavior as an aggregate, taking the information from the atoms, and with the another next level we can consider the macro scale approach, the elements. So in this case we can consider the length scale is millimeter range and the time scale is in the second. So that this time scale or length scale is completely different from this time scale and length scale. There is a huge difference, all these things, but through the multiscale modeling approach we can link the different scale levels, taking the information from the lower scale level to the, we can reach up to the upper scale level, and all the scale level probably the behavior or the calculation theory behavior is different. But if we, as a gross, if we try to predict the multiscale approach, probably we need to link all the different scales. This actually helps to design new material or devices with improved performance. Probably if you look into the very lower scale approach, that actually helps to design the new materials and device with improved performance. That performance can be measured on the higher scale. So molecular dynamics, if we see that explicitly solve the dynamics of the all atoms of the material of interest. So that predicts some certain behavior, the molecular dynamics, that with the forces we can estimate the, in the theory probably we can look into the forces obtained from the interatomic potential, and accordingly we can estimate these things. But at the same time, once it is done in the lower scale, simply if we, lower scale means probably we can look into that in macro scale. If we zoom it, and we can reach it ultimately the lower scale, nanometer scale, and where the macro scale probably we can use the Newton's equations of motion there, and we can predict the behavior. But ultimately that behavior can also be linked with the molecular dynamic simulation that explicitly solve the dynamics of the all molecules of the atoms at the low scale. Now this molecular dynamics applications, probably if we look at the nanomechanics of the deformation, that we have, if we start from the very basic things, that we crystal structure of the metals, crystal structure, we have started actually from the crystal structure of the materials, and we start the very basic model, hard sphere model, that we represents the crystals at regular arrangement of the atoms. If there is a disturbance of the regular arrangement of the atoms, then we consider that the existence of the defect. It can be point defects, it can be line defects, probably can be surface defects as well. So that behavior of the representation of the atoms in a crystal structure, that was on the nanometer scale. Now, or if we on the nanometer scale, if we try to understand the mechanics, so already we explained this thing, this is the regular arrangement of the atoms. Now, if it is subjected to the shear force like that, so over it will create the shear force, it will create some dislocation defects. In this case, it is edge dislocation, and that is a very idealized case. Defects existence in terms of dislocation in the crystals. So, this is the dislocation. Now, there is a slip happens over the cluster of the atoms specific on the slip plane, and this accounted amount is the this is the amount of the shear strain. In this case, overage the shear strain, we consider the amount over the slip plane, and this phenomena we represented in terms of edge dislocation and the screw dislocation, having the defined orientation of the slip plane, slip directions, and representatives of the slip dislocation in terms of the Burger's vector. But this mechanics explained on the nanoscale. So, that is why it is called the nanomechanics, and this slip system of the different crystal structure, all we have already explained this thing, but point is that that explanation, all these things was valid in the nanometer scale. So, that is called, it is called nanomechanics. So, that mechanics is helpful to finally the correlate of the dislocation, discrete dislocation dynamics. So, when the continuous dislocations, and from there we can predict the mesoscale as a grain scale approach, mesoscale, or maybe as a grain scale approach, and from the grain scale we can reach to the continuum scale. So, basically in the materials, the deformation of the metals, if we look in the plastic deformation of metals in the continuum scale, and that behavior, if we try to zoom it, then probably we can reach the behavior of the metals on the nanoscale. So, that is these are the mechanism in the nanoscale, and that we always try to link to predict the polycrystalline behavior, and finally the behavior of the metals in the continuum scale by conducting the simple tensile testing or shear stress of a piece of material at in the scale of the millimeter. So, if we see that molecular dynamics applications specific to analyze the nanomechanics of the deformation. So, in the lower scale level, probably this we are trying to explain the lower scale level. If you see, the initial structure was like that, the first figure. Second figure, if you see that at the deformation of the 0.07, there is elastic deformation happens. Now, once the elastic stress overcome, then at the higher strain level, the plastic deformation happens. So, there is a disturbance, there is a disturbance of the regular arrangement of the atoms, if you see, and here if you see that the reduction of the section, probably I think in continuum mechanics we generally call as a necking, and if we see that another scale, that is the complete the fracture happens, separation of the atoms at the very high strain. So, that similar kind of behavior if we observe in the continuum scale also by considering the simple tensile testing, but here if we see that stress versus time, if we see that graphical plot is not very smooth curve, there is a continuously fluctuating nature of the curve if we observe, because we measure actually we simulate or whatever through experiment, if we measure the time scale was very slow on the picosecond level. So, picosecond level the behavior of the molecules, or probably if we did the molecular dynamics application, so that represents actually not actually the smooth curve or smooth amount of the stress with respect to time, there is a fluctuation of these times. But same experiment if we conduct probably in the nanos, in the continuum scale or millimeter scale, probably that type of fluctuating nature we can eliminate that fluctuating nature of the stress versus time scale. So this is the typical molecular dynamics applications to explain the nanomechanics of the deformation. So of course multi-scale modeling approach, it's a very complex phenomena and there are several challenges also. If we see that the large number of degrees of freedom probably in the atomic scale. So degrees of freedom is very high in the atomic scale. To tackle or handle all this degrees of freedom is not easy to conduct. So to conduct the simulation and the specifically at the very low scale, atomistic scale. Second challenge is that interface. So at the interface there is a mismatch of the dynamic properties. So at the same time, at the interface, how we can link the dynamic properties in the atomic scale to the next scale. Linking this thing is really difficult in case of multi-scale modeling. Third point is that consistent and accurate representation of the mesoscale, microscale and nano level behavior within continuum model. So really difficult to represent all the scale level behavior in one scale. Probably in continuum scale it is difficult to represent all the behavior of the three lower scales. Fourth point is that how to link the different time scale, because atomistic model probably in the picosecond or femtosecond level the analysis, but in continuum scale we analyze in the order of the second. So linking the multiple scale is really difficult. Then interdisciplinary nature of the multi-scale method, for example continuum mechanics, how to apply continuum mechanics, classical particle dynamics, lattice mechanics, quantum mechanics and quantum chemistry, thermodynamics and statistical physics. All interdisciplinary nature of the multi-scale method, linking between these two is a difficulty in the multi-scale modeling approach. Atomic scale plasticity, so plastic behavior prediction of the constitutive laws in the atomic scale is the really difficult. That actually normally atomistic scale plasticity and to link with the lattice dislocations, the plastic behavior of the lattice dislocation, and linking between these two are difficult in the multi-scale modeling approach. Probably finite temperature, these are the issues, entropy elasticity, soft material, there are several issues in the multi-scale modeling. Dynamics of the infrequent events, probably which is not very frequent, but for example diffusion, protein dynamics is a really challenging task in multi-scale modeling approach. And finally, development of the algorithms, issues in the large scale and coupled simulation in length scale and the time scale. And to do that, the development of the algorithm is really challenging task in multi-scale modeling approach. So look into all this problem. Now typical issues very specific to a problem. Say the true coarse scale discretization and coupling between the scale. So if you see the figure, here we are trying to link between the atomistic scale, the representations in the lattice point, and probably assuming the each and every lattice point one atom, but it is not like in the continuum model. But how to represent the interface between these two atomistic model to link and the continuum model. That's why the discretization in the continuum scale and discretization of the atomistic scale are actually different. And because the scales are different, so how the link between these two scales, that is a one significant issue. Second point is the how to handle the interface. But the small and the large scale intersect, therefore handshake is expensive and non-physical, spurious wave reflection may happen also. So probably the technique handshake is required, but how to make the process successful to link these two different scale at the interface. Sometimes double counting of the strain energy, that is one issue. The implementation using of the molecular dynamics and continuum scores is hard probably we need the huge computational resource. Parallel computational method may be required in this case. And other things are that when we try to interface at the link, the two scale at the interface, probably the dynamic mesh refinement, enrichment is more computationally more expensive, and multiple time scale and dynamics of the infrequent events to link all these things is really difficult, and those are the typical issues associated with the multiscale modeling approach. So in a nutshell, or in general, we can say that the difficulties, or in simply we can say the difficulties, the continuum scale and the atomic scale, the represent discretization of the domain, or in these two scales are different. And second point is that how handshaking, that means how we can link the two interface, that is the second difficulties in the multiscale modeling approach. Now, why is the multiscale modeling is difficult? Let us look into details. That probably the wave reflection happens from the molecular dynamics simulation, and of course this is the molecular dynamics wave reflection from the molecular dynamics simulation. And when you try to link the molecular dynamics and the finite element methods simulation, so at the interface, how to represent the wave reflection from the molecular dynamics. Next, the large length scale cannot represent the wave length scales typically found at the smaller length scale. So that is the another issue or difficulties, because large length scale normally we use in the finite element methods, it's not suitable to represent to capture the wave reflection specifically in the lower scale. For example, in this case, the molecular, in the scale of the molecular dynamics. Also, due to energy conserving formula for both molecular dynamics and finite element method is really difficulties at the interface, how to conserve the energy when we try to link these two scale between the molecular dynamics and the finite element. So these are the typical issues. Now, other issues probably we can say in general, we can say that preventing high frequency wave reflection need reduce the molecular dynamic system can be done to behave like a full molecular dynamic system. Reflection of the high frequency waves can lead to the melting of the atomistic system. So that should be very careful to link how we can reduce the molecular dynamic system to link in the to behave like the full molecular dynamic system. At the same time, need for a dynamic finite temperature multiple scale method, that is definitely needed. True coarse scale representation, no meshing FEM down to the molecular dynamics lattice spacing. So it is practically important, it is practically significant that it is not possible to create the mesh in the finite element that actually satisfy to the requirement for the molecular dynamics lattice spacing. So that kind of meshing is difficult to do using the finite element. At the same time, different time steps for the molecular dynamics and the FEM simulation. So time scale for the FEM simulation on the different scale, mesoscale or the continuum scale or micro scale, and the molecular dynamic scales are completely different. So to match between these two also difficult, or linking between these two really difficult in case of multiscale modeling approach. Mathematically sound and physically motivated treatment of high frequency waves emitted from the molecular dynamics region at the MD or FE interface is really need to know. So looking into all these challenges in the multiscale modeling, probably we can now we look into that macro scale approach to materials modeling. Here if we see that materials modeling, so first thing is that macro scale, the fully homogenized description effects of the both grain and subgrain heterogeneities on the material response are implicitly modeled by internal state variables. So fully subgrain heterogeneity on the material response are normally modeled considering the internal state variables. Second point is that by discretizing the explicit representation of the microstructure, the approach loses the capability to model the state of the material in terms of the direct mapping between the microstructure and the properties. So, probably when we try to idealize the polycrystalline behavior using or heterogeneity behavior in the single crystal, and that we try to represent the in a single polycrystalline behavior as an aggregate. In that case, the individual heterogeneity behavior can be lost in this case, and rather than we can use some aggregate behavior on this scale. Typically used to solve the large boundary value problem, since the approach used to reduce number of the degrees of freedoms to represent the material response at each continuum point. So, this is the first idealization, polycrystal idealization. Next, we represent the finite element method, finite element model in the continuum scale. Probably in this case, we need the low degrees of freedom, and we represent the material response at the each continuum point. But mechanical characterization, test, mechanical parameter determinations, that actually play important role, and that we can conduct the experiment and we can represent that behavior mechanical test, and we use the test data of the properties, and we can do the simulation. So, similarly, mesoscale approach to the materials modeling related to the crystal plasticity. Here if we see that explicitly models the discrete grains and the slip system, accounting then for the anisotropy of single crystal properties and the crystallographic structure. So, slip system level actually constitute the equation of the dislocation kinetics. So, if you see the slip system, we use generally the slip system equation as a rate dependent, and the work hardening also based on the phenomenological models we use it and we can predict the slip system behavior of the polycrystalline structure. So, relatively large number of internal state variables for hardening parameters generally used, which implicitly address the dislocation storage and interaction between the dislocations. It is of course more predictive and robust than the macroscopic plasticity, since it explicitly addresses the evolution of the crystallographic structures and models for both anisotropic elasticity and plasticity. However, the approach is computationally expensive. Of course, the mesoscale is the more predictive approach to consider the crystallographic structure and models for both crystal anisotropic and plasticity models. Therefore, but in this case, the approach, of course, the computationally expensive. So, point is that when you try to reduce the scale of the analysis, so it becomes more computationally expensive to capture the behavior of the different length scales or different time scales. Approach used to study the aggregate of the crystals to obtain better understanding of polycrystal behavior. So, better continuum plasticity models probably need it, and that we can enrich the better continuum plasticity model probably by linking into the mesoscale approach, where we explicitly consider different structural behavior, structure directions, and the plasticity law, anisotropic plasticity in the polycrystalline structure. So, that is more predictive to enrich the models for the continuum plasticity model. So, it is also necessary to link the lower scale behavior to becomes the more predictive behavior for the higher scale. Now, why to investigate the crystal plasticity in these scales? Probably see the on the macro scale homogeneous material point most of the we consider, and continuous plastic flow behavior of consider. But if we zoom the scale or if you lower the scale, in the micro scale, if you look, the behavior are different. In this case, the material exhibits actually the inhomogeneity or structure difference is there. Plastic flow occurs on the discrete slip planes. Flow is anisotropic and orientation dependent. Of course, the structure evolves with the deformation. So, all this behavior in the micro scale, probably we can represent all this behavior in the micro scale, which is inhomogeneity, anisotropy, probably we can represent on the link on the macro scale model, which consider the most of the cases we consider the homogeneous material point of view, and of course it consider the continuous plastic behavior, because we have learned that if we consider the crystal plasticity, and we have observed that the plastic deformation of the single crystals may happen of the different orientation, different direction on the specific slip system. So it is generally we consider that is in the discrete system, discrete deformation system, but which is not the case of the microscale application. So that is the one way to link the macro scale to the microscale approach in the crystal plasticity model, by simply averaging the behavior, or we considering the behavior in the different way. For example, the way is like the whether it is homogeneous or heterogeneous, or whether it is continuous or discontinuous. So that type of behavior we need to consider when we try to do the modeling approach relative to the higher scale, specifically in this case the macro scale approach. Now, what are the several importance, how computationally expensive in the single crystal behavior when you try to compute the response of the different stress strain behavior of a single crystal structure. So what are the input in the system? First is the slip system. You need to know the slip system, what was the initial crystal orientation, and the other material parameters need to define. These are the typical input to the system to make the constitutive model for the single crystal structure. Other is what is the deformation rate at each crystal, that information also needed, and what are the kinetics of the deformation behavior. Plasticity, and plasticity means plasticity of the single crystal structure in terms of the flow rule, hardening rule, orientation evolution, change of orientation evolution, all this constitutive information actually link. And finally we can predict the crystal stress and final prediction of the crystal orientation, slip system hardness, and the crystal stiffness. So computationally getting all this information to construct the single crystal constitutive models in terms of the crystal stress, crystal orientation, slip system hardness, and in terms of the crystal stiffness is really expensive, but it is necessary to model for the deformation behavior of the single crystal structure. Now, sometimes or most of the cases the material behavior is inherited by the lower strength scale, that is the actual behavior of the, if we scale down we can look into the actual behavior, actual physical phenomena associated with the materials, and if you go upscaling, a higher scale, probably we are trying to averaging of the behavior and specific to the macroscopic scale. So in the macroscopic motion is distributed among the individual crystals. So in this case, if we see always we try to follow the mean field hypothesis in the macroscopic level, and what is the grain behavior, different state variables we need to explain the grain behavior, and we averaging these things and probably produce the mean field hypothesis, and in this case finally the orientational averaging, and we can predict the macroscopic level at the different state variable. So average the crystal stress to compute the macroscopic stress, we use this complete system, but this satisfies the single crystal constitutive law. Given the standard, actually compute the stress and finally update the orientation. So this is the one scale of approach. Next scale of approach we see that we generally use the constitutive models in the lower scale single crystal structure, and then polycrystalline behavior we zoom it or we focus on the representative material element. That behavior is a representative element, actually behaves as a whole of this specific material, and finally For all these two cases, we generally follow the constitutive model, but finally we try to utilize in the larger scale polycrystalline body as a sample material in continuum scale. We consider the finite element simulation, and that actually needs that we use actually balanced law to predict the behavior of the system. But all these cases, the different length scale, probably we can link into the different length scale and time scale using some multiscale modeling approach. Now question is that how does a constitutive model interface with the displacement based finite element simulation? If we see that, if we consider that first we take an increment of the strain step, assemble the stiffness matrix, then we compute the stress corresponding to be imposed of the strain increment, and the stress is handed back to the finite element core to see if there is a weak form of the equilibrium or linear momentum equation is satisfied or not. If it is not satisfied, then adjust the strain step and compute the new stress increment and repeat until the weak form converges. So then once we get the converged solution, then we shift to the increment to the next time step and shift to the next step. So incremental strain step, estimate the stress value output from the system, whether it is satisfying the equilibrium equation or not. If it is yes, then we can increment that time step, probably next level. If it is no, then again we have need to adjust the strain rate. So this is the typical approach of constitutive model interface with the displacement based finite element simulation. Now in the simulation, many tensor constitutive equations are reduced to a set of equivalent scalar equations to be solved. For example, when we try to analyze the continuum plasticity model, we assume that there is a effective stress or equivalent stress value, and sometimes we call the von Mises equivalent stress value, and that equivalent stress actually the equivalent form of the representation of the stress step. So if there is a 9 component of the or 6 component of the stress is there, that 6 components we can represent one single value, that is called the effective stress or the equivalent form of the stress. So that is used to predict the law in case of plasticity model. So similar kind of things we can use it, or that means some tensor we can convert it in terms of the scalar quantity, and we can use to conduct the or to modify the different law or use in the constitutive equation. So isotopic constitutive laws relate the magnitude of the strain rate to the magnitude of the stress. So relate the magnitude of the strain to the magnitude of the stress. But anisotropy stress tensor components actually vary independently. So crystal plasticity models actually relate the rate of the slip along a slip plane. That slip plane we can consider as a scalar quantity to the shear stress acting on the plane. That can also be another scalar quantity. So that shear stress is finally can be constituted with respect to the rate of the shear strain. So anisotropy arises because the crystals and their respective slip system can be oriented differently. Because of that, the anisotropy actually exists. So that different stress values at the different crystal systems can also be equivalent form, or in terms of the scalar quantity can be represented in the single link with the single stress state or scalar values of the component. So that is another approach that we generally follow in the crystal plasticity model. The microscopic motion, if we see that inherited from the continuum level, if we consider the microscopic motion actually inherited from the continuum model. So how we can explain like that? The continuum model in the sense, for example, simple, if we conduct the tensile test of a specimen of a sample, so we can execute the tensile stress and corresponding stress strain diagram. But with the application of the external on the samples, that what maybe the changes happens in the microscopically. So if you see the microscopically, and if you try to explain the microscopically the single crystal behavior, here see that single crystal experience the macroscopic motion. How is it like that? Because recall, all motions can be broken down into the pure shear and the rotation. We have explained that when it is subjected to, specimen is subjected to some tensile loading, the several slip system actives at single time. So there is a constant, or that is a restriction of this direction of this load, and if we make some constant motion of these things. So from the theory of the plastic deformation, slip happens in case of single crystal structure. You see that it is, if you put the constant, then there is maybe some slip will happen with the along with the rotation. So the crystal can only shear along the slip planes, but the specimen axis remains the fixed. So crystal lattice also needs to rotate itself. So it is subjected to rotation itself. So we can make the conclusion that this microscopic rotation or microscopic motion is actually inherited from the continuum scale. So we need to consider that. So that macroscopic motion we actually need to consider when we try to make some constitutive model in the crystal plasticity. So crystal motion is expressed in the rate form, and the expanded related to the set of basis functions are tied in the lattice frame. So different frame, if you see the crystal motion is accommodated by the slip plus a rigid lattice rotation. So the crystal velocity gradient has contribution from the plastic slip. So both plastic slip as well as the lattice spin. So that two components we can consider in this case to explain the motion of the in terms of the rate form. And why? Because this is the reason sometimes we represent the hardening law in the crystal plasticity in terms of the rate dependent. So both crystal motions and occurs by the discrete slip on the slip plane. Now tensor constitutive equations are reduced to a set of equivalent scalar quantities. So we have already explained that sometimes we represent the stress tensor in the form of the equivalent form of the equation, that is a single scalar quantity. So that can be said that slip systems are activated when the resolved shear stress approaches the critical value. That is true. But the rate of the slip is related to the critically resolved shear stress acting on the plane. So that is the relation between the shear stress and the rate of the shear strain. And accordingly, we can consider the kinetics as a fixed state. So if you see the figure right hand side, different values of the M, the relation between the stress and the strain rate, if you see this constitutive relation can vary depending upon the different values of the M. So with this behavior, probably it is possible to evolution of the state from the hardening rule. The resolved shear stress and the slip shearing rate can be written in terms of the crystal stress tensor and the crystal deformation rate tensor respectively. So I am not going into much details, a mathematical derivation or related to all these phenomena, but ultimately we can form the constitutive relation in terms of the shear stress and the rate of the shear strain, and accordingly we can evaluate the hardening rule even in the crystal plasticity model. Similarly, alternative averaging methods have also been developed in an attempt to minimize the number of state variables. That is also another important issue in the microscopic model, that if it is possible to reduce the internal state variables, so that can be done, some discrete averaging of the certain of the properties. So that analytical solution or discretization space, these are the that we can derive the functions, orientation distribution functions that actually try to description based on the analytical solution or discrete distribution space. It is possible to reduce the number of state variables in the microscopic model. So this is the discrete model averaging strain rate, simply averaging of these things, polycrystal stress, we can make it through averaging, and structure is a set of Euler orientation angles of the each crystal. So that are the typical discrete averaging, discrete model averaging the all the state or properties. Now we come to the second part of these things, that modeling of the engineering materials and what are the different approaches for that. So if we see that modeling engineering materials, so there are different scale. We have explained that several times that there is a different length scale and the time scale, the quantum mechanics, molecular dynamics, mesoscale and macro scale. Probably these are the 4 or 5 scales can be used to explain the multiscale modeling approach. Now here if you see the representations of this scales is this 10 to the power 23 atoms, but probably in this case 10 to the power 0 to 2 atoms in the quantum mechanics. That is a representative volume in terms of atoms. And if you see the scale is a very 10 to the power minus 12, 13, and here it is the micrometer or meter scale or maybe millimeter scale. Now about the quantum mechanics, molecular dynamics, based on the mechanics or basic physics on that, the nanotechnology can be explained. Then based on the mesoscale application, the microtechnology has come out, and finally macro scale approach, the structural mechanics or continuum mechanics approach can be explained over the different scales. So scales, multiscale analysis, so accordingly there are different levels of the technology has been developed. Now in general, the multiscale modeling approach, the computational modeling generally aims to developing the systematic techniques for bridging the scales. For example, between the atomistic models and continuum models, in order to increase the speed or enable dynamical calculation. That is a basic objective of the multiscale computational models. Continuum level models of course can simulate larger volumes of the materials, which is not possible for the molecular dynamics. So typically at the expense of the accuracy. Of course, when we consider the continuum levels of the model, the large volume of the material, try to focus on the analysis, it's not possible to capture exactly the phenomena in the lower scale quantum mechanics or the molecular dynamics. So that's why continuum level models always we do the large volume of the materials analysis, but at the expense of the accuracy. Conversely, the nanoscale models can accurately capture the small scale phenomena, small scale features, but actually computationally too slow to simulate as compared to the large volumes of the material. So computationally expensive large volume of the materials is really is a main obstacles that when you try to capture the nanoscale phenomena. Therefore, the goal of the multiscale modeling is to take the advantage of the fact that in many systems only a small percentage of the total region is of interest. So strategically very small component or small part of interest really we can link the different scale to capture the features or at the different scale, and that is the basic philosophy of the multiscale modeling approach. So, but main challenges multiscale modeling approach is the determining when the regions are the simulated with the continuum model or the nanoscale model, but adequately model the transition region, that is the main two obstacles related to the multiscale modeling approach. One approach is that explain that concurrent multiscale modeling approach and hierarchical approach. So here we will try to look into the concurrent multiscale modeling approach. One thing is the strength of material is actually dominated by the existence of cracks or other defects or flaws. So probably that concurrent multiscale modeling approach will try to explain considering the strength of material or formation of the cracks during the deformation of the metals. Cracks and similar defects actually lead to the stress concentration, which in turn actually lead to the nucleation of the dislocations or generation of the material surface. So, generation of the cracks can be explained like that. There is a nucleation happens, so it starts from the nucleations and finally the development of that small crack, and that after that there is a fracture happens, the samples of the materials of interest. Now, defects actually lead to the highly localized region in materials, and which material undergoes the strong deformation. Therefore, division of the computational domains into different regions of the different accuracy is possible depending upon the strain gradient. So, probably we can link the atomistic behavior in the scale of the continuum when you try to analyze the fracture mechanics to get the actual information, what is the cause of the fractures in the scale of the molecular dynamics or in the scale of the next level of the scale. But how we can do that? That continuum displacement field, if you see the atomistic region, time steps here, this is the atomistic region, time step here is around of the order of femtosecond, but in other case continuum region the time step is the order of the greater than millisecond. But atomic displacement field probably related to the first oscillations of the atoms. Now, how we can link these two scales through the multiscale modeling approach? Normally, we avoid the wave reflection at the interface between the molecular dynamics level and the finite element interface. It is possible to make the seamless interface that because wave reflection may have dramatic impact on the results, sometimes it leads to the melting. So, make seamless interface probably the one challenge for the multiscale modeling approach. Several attempts earlier, but normally people follow the handshaking between these two link between these two scales of the analysis, but for the handshaking we need the physical insight of the mechanism of the process. Now, handshake region, we can coupling between the regions of the different level, scale or accuracy can be achieved using the handshake regions. So, or that method. In this case, the exchange information associated with the each modeling is required. So, here the translation rules or which algorithm is needed, specific algorithm is needed to exchange the information at the handshake region. So, what are the typical? So, if you see the different property and the different scale, atomistic scale and continuum scale, if you see the temperature, atomistic scale, the property temperature represented by random velocities, but in continuum scale probably more associated with the thermodynamic energy. So, the scale of analysis at the two different scale, the property is represented or associated with the different levels. Displacements, the atomistic displacements is a fine displacement in atomistic scale, but in continuum scale the continuum displacement probably it is not very fine, coarse. So, in this case we can consider atoms as not the main elements, but atoms can be considered as a subset in the continuum scale. Particle velocity in atomistic scale includes the high frequency vibrations, but continuum scale only low frequency vibration relevant. Particle forces probably in atomistic scale represented by the atomic forces, pointwise and atomic forces, but pointwise it is discrete. But in continuum scale the particle forces can be represented in terms of the continuum forces, but that is the distributed. So, there is a huge difference to represent some of the different property at the different scales. Therefore, it is necessary to develop the filter algorithm in the handshake region is essential, and also the energy conserving formulas. So, energy conserving formulas at the handshake regions for both molecular dynamics and finite element method when you try to link between these two scales. Now, the two scales of analysis, continuum and atomistic scale, of course difficult, but since atomistic contains information that continuum does not provide, or only the indirectly, either in terms of temperature. So atomistic design, that is the one thing point, and then therefore averaging or the stress, displacement and the statistical mechanics, once real dynamical trajectory is known, then we can, using the filter, we can get the useful information. But still boundary apex is very critical, this to linking between these two scale. Domain decomposition, one of the probably algorithm in multiscale approach is the domain decomposition algorithm. So it's as simply as that first step of the concurrent multiscale model is typically decomposition of the computational domain according to the several criteria we can follow. So how we can decompose the different domains? So there are several criteria. First criteria is the foreign atom types. Probably the only method A treats atom type Y and XY interactions. Second is the strain, atomic strain or the stress localization state. Based on, we can divide the different domains. Large forces between the atoms suggests bond breaking or bond formation. So that can be based on that criteria, we can divide the different domains. Large strains or cohesive energy based on that, or simply geometric criteria or an information, that means either interfaces, boundaries or others. On that criteria, there is possible to decompose the different domains. So finally, the union of the many domains associated with the fine scale particles represents the area treated by the fine scale method. If you look into that figures, that different zone of interest having the different following the different criteria. So it is possible to discretize the domain of small domains, and that actually union of the whole domain, and accordingly we can analyze, we can predict the behavior. So individual for individual domain, probably we can use the different theory in that according to that scale levels, and finally we can link it. So this is the one way, simple way, the domain decomposition algorithm. Another is the concurrent multiscale method, the coupling of the length scale. So that is typically called the MAD method. So it is a typical links between the finite elements, molecular dynamics and the tight binding, all used in the single calculation. So that MAD method, actually it's called macroscopic atomistic behavior, and the dynamics behavior is captured in a single calculation. So tight binding means, here tight binding model generally is an approach to the calculation of the electronic band structure that is used. So in MAD model or maybe MAD method, probably we can use all these three different scales information: macroscopic, atomistic and the dynamics. Atomistic is used to resolve features of the interest, for example crack, and continuum used to extend the size of the domain. So taking the advantage of these things, continuum and atomistic and individual area of interest, merging it, this thing, that the MAD algorithm or MAD method has been developed. So this is a schematic diagram for the MAD method. If you see that simply coupling, how it is coupling the tight binding, I think tight binding, molecular dynamics and the finite element method. If you see that things, the transition regions are very thin, desired of course due to the computational expenses. So displacement and velocity link between the scales based on the kinematics, and the time steps governed by the atomistic scale or tight binding and molecular dynamics, and that time scale generally follow in the order of femtosecond, but it is limited to up to nanoseconds. Except wave reflection from the finite element and molecular dynamic interface, probably this method works well. Now if you look into that, another basic method, that is a quasi-continuum method, that is also coupling the empirical potential to the continuum models. So key idea is the Selective representations of atomic degrees of freedom, not necessary to consider all degrees of freedom in the atomic scale. Probably if we more selective, we can that selective scale probably representative on that molecular dynamic scale. Therefore, instead of treating all atoms making up the system, a small cluster of subset of the atoms is selected to represent by appropriate weighting the energies of the system as a whole. So, only system of the atoms represents the whole energies of the whole system, and in this case if it is needed we can use the appropriate weighting of all the atoms. Based on their kinematic environment, the energies of the individual representative atoms are computed either in non-local fashion in the corresponds with the straightforward atomistic methodology or within a local approximation as befitting a continuum model. So, assuming the local approximation of the befitting of the continuum model, since few atoms represent the whole system, the representation is of varying density with more atoms sampled in highly deformed regions such as near defect also. It says strategically, if high deform or high deformation gradient exists, which that point probably we can increase the represented atoms more to capture the phenomena more precisely, and correspondingly the fewer or less deformed regions further away is adaptively updated to the deformation evolves. In that way probably we can conduct these experiments, probably that is the basic philosophy of this method. Now, quasi-quantum method, quasi-continuum method actually provides the alternative to the handshaking. We see the basic idea was like that: obtain the finite element stiffness matrix on the fly based on the atomic lattice or potential, not required any prior assumptions. Zero temperature relaxation technique, this is elastic energy used in finite element region is computed by applying the finite element method interpolated displacement field using the Cauchy-Born rule, for example, to a reference system of atoms interacting by the molecular dynamics forces based on the finite EAM potential. But difficulties is that no thermal fluctuation since atoms are at reference positions. Therefore, sometimes ghost forces due to the discreteness of in AP system, and the problem that the molecular dynamics probing is based on the discrete displacement field. So, if we look into that one continuum model will link the MD model probably based on the discrete displacement field, and that using following the Cauchy-Born rule provides the constitutive equation on the fly. So, Cauchy-Born rule states that the infinite crystal underlying each continuum particle deforms according to a local uniform continuum deformation gradient F that is used to extract the constitutive law. So, another example application, that is deformation of the thin films. Probably if we see that the biaxial loading by thermal mismatch of field and the subsequent material. So, actually high stress caused the severe problem during the operation of the device. So, schematically if we see the biaxial stress subjected to a polycrystal structure. Now, deformation is localized, actually the deformation is localized at the grain boundary, and so in this case the dislocation and the grain boundary interaction is important to know. And if we see that idealized system in the polycrystalline form, probably we can represent these things stress, and if we see that near about the grain boundary there is a cluster of the dislocation, or probably there is a deformation is localized near about the grain boundary region. So, it is important practically because submicron copper film becomes critically important in the next generation integrated circuit. So, in this case probably the combined atomistic regions embedded in the continuum regions, and by following the multiscale modeling approach only we can address this kind of problem. But non-local QC methods, in this case if we see it does not use the Cauchy-Born rule as does the local QC method, but instead use full non-local representation to determine the forces. So what are the features of this non-local QC method? Here if you see that it is truly seamless, there is no boundary present between the atomistic and the continuum regions, but it's a very smart scheme to avoid the double counting of the bonds. So use the explicit expression of for forces on the nodes, atomic limit, each node and one atom, evaluate the small cluster around the node J. Here if you see that typical cluster, there is no overlap and it's a overlapping cluster. So this is basically one kind of non-local QC method, and most important features is that no boundary present between the atomistic and continuum region. So this approach can be used to solve the multiscale modeling problem. Now another approach is that is called CAD approach, the coupling discrete dislocation dynamics with atomistic simulation. Here the method provides the interface of the DD regions with the atomistic region. If you see the zone 1, 2 and 3, we can represent the different way. That coupling achieved by the nodal displacement in the handshake region. So in terms of the atomic displacement, forced to agree with the finite element displacement and paired atoms to agree with the finite element displacement. So paired atoms actually agree to the finite element displacement, but coupling happens that in the handshake region, so that atomic displacement is basically agreed to the finite element displacement. So this is the CAD approach, and we use the coupling discrete dislocation dynamics with the atomistic simulation. If we see that CAD method schematically, that this is the interface atoms and right hand side is the continuum region here, and there is a paired atoms. So coupling similar, here the coupling is similar to MAD approach, but it is in the quasi-static conditions. Now another method is that is called the bridging scale method. We use the multiscale modeling approach, that actually coupling the atomistic scale to the continuum scale at finite temperature. So in this case, the finite element representation exists everywhere in the domain, even where MD is also present, molecular dynamics also present. So use the projector operator to represent the displacement field as the orthogonal combinations, small scale and the coarse scale, both we use it. But what are the advantages in this bridging scale method? The atomistic and continuum scale do not have to be integrated using the same time step as we generally is done in the MAD scheme. But high frequency oscillation naturally disappear when they leaving the atomistic core region and via the impedance force. Atomistic region senses finite temperature in the finite element regions via the stochastic force. So this is another typical bridge scale method we generally follow in the multiscale modeling approach. And if we see that area of interest, for example, if we consider the example of the crack, and that molecular dynamics, if we consider the representative of these things, right hand side is the finite element zone in the continuum scale. So if we add these two, probably we can represent the MD plus APM, this zone, and that is the equivalent form, and we represent the correctly that the force actually F and T. So reduce MD and impedance force plus APM is represented correctly this way. So this is the other way to link bridging the different scale following some specific strategy. So these are the all methods. I try to explain the different methods just to overview on the different methods that actually generally use in the multiscale modeling approach. So to do that, we can conclude the this section like that. Normally concurrent scale coupling techniques have evolved significantly in the past decades, and most of the method developed on the concurrent scaling approach. But now robust and stable methods become available, applicable to an increasingly wide range of the problems. So many development also be done, robust methods also be done. Nowadays it is available. Finite temperature applications of course remain a subject of ongoing research still, and concurrent multiscale methods of course are readily available, and probably you can simulation codes can also be downloaded from the obstacle different methods. People find interest to do that, but some researchers still think that concurrent coupling is really difficult and associated with many numerical and physical difficulties. So therefore they favor the hierarchical approach methods as a cleaner way to convey the information according to the scales. So thank you very much for your kind attention.